So light traveling in air strikes a slab of glass at an incident angle of 60 degrees, and then it enters the glass, and the index of refraction of the glass is 1.5. So in part A, draw the resulting path of the light beam on the diagram. So the first thing to note is that air has a lower index of refraction than glass. Air is, we're going to just say 1.0, and the glass is 1.5, and then it goes back to the air, which is 1.0. So when a beam of light travels from a lower index to a higher index, instead of going straight through like this, we know that going from low to high, it bends toward the normal, which is this dotted line. So the light beam is going to go this way. When it hits the glass, it's going to bend toward the normal over to the other side, and then when it hits this side, it's going to bend away from the normal. So the first beam inside the glass is a straight line going across like that was bent slightly toward the normal. Then if I draw a dotted line to represent a normal on the other side, instead of passing straight through this one like that, it's going to bend away from the normal, upward like that. So I can draw the final beam coming out the other side like that. For part B, what is the angle of refraction in the glass? So it's asking specifically for this angle inside the glass between the beam and the normal. So what is this angle right here? And to do that, we're going to use Snell's law, which was n1 sine of theta 1 is equal to n2 sine theta 2. N1 is the index of refraction where the beam originates, which is in this case in the air, so that's N1, which is 1.0. The N2 is where the beam ends up, is 1.5, and the incident angle, the theta 1, is 60 degrees, and we're trying to solve for theta 2 right there. So since I'm solving for the theta 2, I'm going to start by dividing both sides of the equation by n2, so they cancel out. So the sine of theta 2 is equal to all of this stuff, which I'm just going to plug the numbers in. N1 is 1 times the sine of theta 1, which is 60 degrees, divided by the n2, which was the 1.5. So 1 times sine of 60 divided by 1.5 is equal to, and I'm actually going to round this number to about 5 decimal places just to make the final answer a little bit more accurate. So it's 0.57735. That's what the sine of theta 2 is equal to. So if I want to get theta 2, I would just take the inverse sine of that. The inverse sine of 0.57735 is equal to approximately 35 point, and I'll give this one a few decimal places as well, 264 degrees. So that's the angle it makes with the normal once inside the glass. Then the light emerges on the other side. It comes out into the air. So for part C, we know that this angle right here is exactly the same as this angle. That's one of those properties of geometry. They're alternating interior angles. So this angle is the same as this angle, and we want to figure out the angle of refraction over on this side. So now the 1.5, the glass, is going to become the new N1, and the 1.0 is going to become the N2. The incident angle is now going to be the theta 1, which is this thing, and we are trying to solve for the theta 2, the angle that it emerges back into the air. So you could set up Snell's law again. N1 sine of theta 1 equals N2 sine theta 2, And if you solve this equation for theta 2 the exact same way we solved the one above, you would find that theta 2 turns out to be exactly 60 degrees. The same angle that the beam entered the glass with.